1, 2, 3. Okay. All right, guys, so let's begin. Hi, everyone. I'm Eugene, and today I'm going to talk about scala.meta, our next generation metaprogramming framework for Scala. When saying the words of introduction about what this scala.meta thing is, I'm usually talking about metaprogramming, what that is, and how metaprogramming is about manipulating programs, and how scala.meta is supposed to make this easy in comparison with the tools that we have right now, for instance, Scala Reflect. But what I'd like to mention today, especially, is that scala.meta is more than just macros. So since my earlier work in the community, it was mostly about macros, people think that scala.meta is just about them. But actually, we're especially interested in doing tooling. So it is very important for us to come up with such an API that people could use for all kinds of metaprogramming tasks. For instance, writing code analysis tools, maybe code coverage tools, things like this. And also, macros are, of course, important to us, but they're just another use case. As we figured out, scala.meta is a metaprogramming API. And it consists of two big parts, things that manipulate syntax and things that manipulate semantics. In the first two parts of the presentation, we will talk about them, and we will see how you'll be able to see for yourself whether they live up to the expectation of being simple and robust. Afterwards, after we get into some details, we will go and take a look at the live demo, or maybe two of them. It depends really on how well I'm going to do with time. And finally, we will conclude with the concrete roadmap. So we have plans for the 0.1 release. And now we know exactly what we want to have there. And I'll elaborate more on that in the end of the presentation. OK, so let's proceed. Before we go into the details, I would like to mention our big team of people who have already contributed to scala.meta. It's a huge project, and I'm very lucky to have people who are interested in hacking something. So this includes my colleagues from EPFL, our students, and external contributors from essentially all around the world. So thank you guys for making this possible. And now, without any further ado, let's proceed. So syntactic API. When you're doing syntactic things, you're interested in figuring out the shape that the program has, seeing whether it has class definitions inside, seeing whether it has methods, maybe some partial functions, and so on and so forth. So really, you're looking at the superficial structure. And this kind of stuff is really easy with scala.meta because we specially designed our trees to be convenient to the users, as opposed to be convenient, for instance, to compiler writers or those who are familiar with compiler internals. And secondly, we did our best to come up with a really simple API. So in order to get started with syntactic things, in scala.meta, you actually need two imports. So just two imports, you don't need to create any globals, any toolboxes or REPLs, nothing like that. So first you import scala.meta._, which brings all the trees and parsing APIs. And finally, you need to specify a dialect. Since scala.meta is supposed to be a platform-independent metaprogramming solution, we sort of look forward to new dialects, new variants of Scala that may appear in the future. For instance, Scala 2.12, or I don't know, Dotty, or something like this. And therefore, we sort of future-proof our API towards that. Since currently we'll be looking into Scala 2.11, let's just import this dialect and forget about this for the rest of the presentation. Let's talk a bit more about the design goals for scala.meta's syntactic APIs. Well, first of all, based on our experience with Scala Reflect, we would really like to keep all the minor syntactic details that the user has written in their program. We would like to keep it, not to throw it away, not to desugar it, not to ignore it as irrelevant, for instance, like the current compiler does with comments. We want to expose it all to the users. When we just started the project about a year ago, in our previous in our previous talk in ScalaDays Berlin, we knew very well that we wanted this to happen, these design goals to happen, but we actually didn't know how. And the realization, it came to us much, much later. So maybe you know that, maybe you don't, but actually implementing these goals, it requires introducing a new concept, which is typically not present in the metaprogramming APIs. And this concept is tokens. So what are tokens? Let's just go and take a look. So you could very well open the REPL and just type this thing right in. So this is the kind of convenience and accessibility to the users that I was briefly mentioning before. So it's our goal, and we really want to make things easy. So in order to get tokens from something which can be parsed, which can be tokenized, you just call tokens on it, and the standard type classes will take care of that. If you don't want something else, you can define your own type class instances. But the main API, the core API, it should be very easy. So back to tokens. Let's see what this thing returns. So if we take a look at what happens, we will see that tokens, they cover essentially everything that's written in the program, virtually everything. Any white space, any comment, any keyword like we can see here, class and def, then all the names that we can see in blue, so in particular the name of the class and the name of the method. Also all the punctuation, like curly braces, this equal sign, and so on and so forth. So as I mentioned, there's also white space. So white spaces are not printed because, well, they're white, but still you can see that there's a lot of them. And finally, such exotic things as the beginning of file and end of file. These are rarely necessary, but when they're necessary, it's quite important. So then, what can we do with these tokens? And here I will give a few examples of quite cute applications of this technology. So why do we need this abstraction? In fact, it turns out that it's very, very practical. So let's take this use case, which is really hard to pull off in Scala Reflect. So how do we distinguish class C without any body and class C with an empty body, that is with empty curlies? So as we see from the printout, scala.meta can successfully do that. But how does it actually do it? Because in both cases, we don't have any statements in the body. So what's going on here? Well, actually, tokens, they answer our question here. So when we parse the trees, for every abstract syntax tree that we generate, that the parser generates, we remember all the tokens that comprise it. And then, thanks to those, we can really discern these two very similar use cases. So as you can see, the second option with empty curlies, it actually has those curlies marked in blue, and it actually has them. So this is how we can distinguish these cases. And that's an important step ahead in comparison with what we have in the current metaprogramming APIs for Scala, because that's simply impossible there. And definitely sometimes you don't need that level of detail. For instance, if you're writing macros that operate on the semantics of the program, but sometimes you do, for instance, when writing a refactoring tool, and when you do, it's really a pain to fight with Scala C. Another very, very important use case for tokens is automatic positions. So if you have worked with parsers, if you have written a parser yourself, you probably know that positioning and consequently error reporting is quite hard. One typical approach, if you write a parser by hand without using any combinators, is to just have some abstraction for positions and then manage these positions yourself. So if your parser creates a tree, then just compute a position that this tree should correspond to, and then you assign it explicitly. Well, since you're doing it by hand, and since sometimes parsers desugar the trees, it becomes really hard to understand which trees correspond to which parts of the syntax. But here, since we have a dedicated abstraction, a dedicated lower level abstraction, which is lower than trees, called tokens, we can delegate this task completely to them. So let's again take an example. So you've already read this slide. You can see that we have a class there, and we have a method in there. So how do we figure out its position? Turns out it's quite simple. So the parser, it associates tokens not only with the top level tree that it returns, but with all the subnodes as well. And these tokens, they remember their own positions in the file. So as we can see, this method, it remembers that it starts with def and ends with 2. And this range, it also includes white spaces, name x, the equal sign. But the main point here is that if we want to figure out the range that the tree occupies, we just take the start of the first token and the end of the last token. And here we go. So in the parser, we don't have to manage positions anymore. So we just remember tokens, and the rest comes for free. This is really, really important because in Scala Reflect, even with the range positions enabled, sometimes positions are hard. Maybe we will see some details about that today in the demo. And the final use case is it's more technical one. It's about internal implementation details of quasiquotes, but don't be scared. I'll try to explain it in a few steps. So quasiquotes, they let, well, quasiquotes in Scala Reflect that we're currently looking at, they provide a really simple API to create abstract syntax trees. So here we can see how we create a tree that corresponds to a class with some custom name that is unquoted into this quasiquote. An interesting point is how we implement that unquoting actually. Because Scala itself, it does not have syntax for unquoting. The support for that is provided by string interpolation. So what we do under the covers is actually quite curious and also quite dirty. So when we want to process this quasiquote, what happens is that we replace all the locations where we want to insert something with some freshly generated names. And then, after we parse the tree, we look for everything that reminds these fresh names. So it can be a name, it can be an identifier, it can end up in all kinds of weird places, and we have to handle all that. So that's the unfortunate consequence of the current parser situation in Scala Reflect. But with tokens, and now we switch back to scala.meta, with tokens we can improve on this. So actually here you can see exactly the same quasiquote that creates a class that uses a name and inserts it into the quasiquote. So what happens here is that we don't create any synthetic things. We actually don't create any strings that we want to parse. We create a stream of tokens directly from the quasiquote, directly from the input. And we have a special token that says that it corresponds to unquoting, to inserting things into quasiquote. And then our parser, this is a secret that I haven't mentioned before. Our parser, it doesn't take strings as input. It doesn't take arrays of characters as inputs. It actually takes tokens. So the parser is very well equipped for this kind of task, and it produces the expected result without any hacking, with fresh names and with figuring out where they ended up. So just to sum it up, in our syntactic API, we have abstract syntax trees that have precise positions that capture all the details of formatting, of comments that the user has written. And all that becomes possible because we found a new, we think, fundamental abstraction for syntactic APIs, that is tokens. Now that we've become familiar with the syntactic aspect of Scala.meta, let's take a look at the semantics. So semantic APIs, they tell us about the relations between the elements of the program. For instance, with a semantic API, it's possible to resolve a reference to see which definition it refers. It's possible to figure out types and then to ask for members of those types. It's possible to check subtyping relations and so on and so forth. The list is really big. And unlike with the syntactic APIs that we've implemented completely in-house within Scala.meta, implementing the type checker for Scala is a really big task. So therefore, we piggyback on existing implementations that are called hosts. We'll probably revisit them later. But for now, we need to know that in order to use semantic APIs, we need an import again, this underscore import, and something that's called the context, which encapsulates essentially the implementation of the type checker. So here I'm creating a project context, and then the parameters are omitted, but there you can provide sources and dependencies of those sources, much like you specify projects in SBT. And then, after you have this implicit value available in a lexical scope, you can ask for all the sorts of information that I mentioned. So you can, for instance, take a name, and ask what it refers to. These contexts, they can come from multiple places. So this MK project context, it's interesting for standalone applications where you don't run inside the compiler, for instance. But if you're in a compiler plugin, you can actually reuse the Scala tools in a C global that the Scala C provides. And you can create a context based on that. Also, if you write in macros, if you write in scala.meta macros, maybe we'll have time to take a look at them today, then you will get a context automatically provided by the macro engine that you'll be running in. And finally, our context API, we think so, it's quite reasonable. It contains about a dozen methods, and it is reasonable to think that it can be implemented by someone, unlike the APIs that we have in Scala Reflect. So really, these contexts, they can come from a lot of sources. And this is our plan towards having a platform-independent API. As long as your platform provides a context for scala.meta, then your users can benefit from it. And the metaprograms, for instance, macros or tools that you have written against scala.meta, they will be working with another platform as long as you have a context for it. You don't have to implement anything else. So let's go to design goals for the semantic API. Actually, again, we draw inspiration from our experience with Scala Reflect. So in Scala Reflect, there's a wealth of different reflection artifacts that model different semantic information about pieces of programs. So we have symbols that represent definitions. We have types, which, well, are about types. We also have annotations, constants, and all that thing. And based on our experience, this might be quite confusing to the new users. And therefore, we decided to collapse all this space into just one concept. So we represent everything with its abstract syntax. So if you have a definition, for instance, a method, then you just have a syntax for it. So if you want to take a look at the signature of the method, you just figure out the parameters and the return type of that abstract syntax tree. And this is it. So you don't have to have a separate universe for this. We will take a look at concrete examples in like 5-7 minutes. And again, this was quite a noble goal when we set it, but we had no idea how to do this. And it also required a new level of abstraction, which is actually names. So our idea is that if we have support for first-class names, then that's all that it takes to implement semantic APIs. So let's see what it entails. What's so special about names? So let's go back and reflect upon what we see with Scala Reflect. If we take a look at how a tree for a simple class is going to look like, we can see the internal structure of this tree using showRow API. Then it's going to be, well, quite a long printout. You don't have to understand all of that or to even, read all that. Let's just try to figure out how we do names here. So which parts of this printout are relevant to either definitions or references to them? So if you're unfamiliar to Scala Reflect, that will be even better because you will have a very valid hypothesis. Well, here in blue, we have all these type names, term names. So maybe these are the things that are used to connect the dots, that are used, for instance, to say that x on the right-hand side of y actually refers to the method x in class C. But unfortunately, in Scala Reflect, names are just, just intern strings. So they have nothing to do with that. That's unfortunate. So let's just omit them here. And what actually happens is that definitions, they're represented with classes that are subclass of member def. For instance, def, it represents a def. And the class def, it represents a class. Something like this. And then references to those definitions, they're typically idents or selects or something like this. So this is quite a bunch of concepts. And now let's see how we manage to simplify this with scala.meta. So if we take a look at the similar printout for scala.meta that uses the showRow API, which is expressed a bit differently but does exactly the same, we will see that both the definitions, like the definition of class C or method X, and usages of those definitions, they're represented with names. So fundamentally, if you write class C, then this C is the name of the class. And that's essentially its identifier. Of course, we don't identify things just by their names. We also remember the context, but you get the idea. The main point behind scala.meta is that names are a fundamental abstraction for semantics. So once you know what the names mean, that's all that you have to know about your program. And this might sound a bit weird, so let's take a simpler example. So let's see a simple and common type, list of int. So how do we figure out what it means? Well, as humans, we know what list means, and we know what int means. And therefore, we can understand the meaning of the program. And that's exactly what scala.meta does. If we see the structure of the tree that corresponds to list of int, then we will see the two names that we were just talking about, list and int. And if we print out the semantics of this program, then we will see that all the semantic information is concentrated in names. So here we see that list, which has a squared bracket 1 next to it. It corresponds to a definition list in the Scala package. And then we see that int corresponds to a class in the Scala package again. So that's it. That's all that you need to know to understand the program. And that's all that scala.meta needs to know in order to provide a platform-independent representation for all the semantic information, like types, subtype relations, and so on and so forth. All right, and of course, now let's see how it extrapolates to other APIs. So I promised a resolution of references. And well, here we go. Let's take a Scala collection immutable list. Here we have 4 names, by the way. And let's take a look at the definition that it refers to. So let's just say .defin. So what happens under the covers is that scala.meta will take a look at the name, a list that we're inspecting, and then it will read the semantic information from there. Or it will ask the host for it if there's nothing there. And then we will get the member as it was defined. So as you can see, we get the list, which extends seek factory and serializable as well. So just as it was written. And then from a member, from a definition, we can go back to a name. So as I mentioned before, when you write a definition, then the name is the identifier. And then when you say result3.name, you really get a reference to that list. So you can take this reference and insert it somewhere. And that's all that it takes. Also, again, thanks to names, you can do all kinds of stuff. So another example here would be taking a list of members. So let's again go for this Scala collection immutable list, and let's ask for a list of its defs, for instance, called apply. So that's what the first line does. Again, what's required here is just knowing what list means. And then the rest Scala Reflect can do. Also, there's a whole bunch of semantic things that can be done. For instance, figuring out parents of a class, or figuring out which members are overridden by a given member. And all this is enabled in the semantic API. All right, so let's just recap what useful effects we got from introducing another fundamental abstraction. So first of all, with names, we've been able to really unify trees and types. So as I mentioned before, when I was showing this example with t list of int, I didn't mention that it's a type that is some special structure which is different from an abstract syntax tree. So it's tree as well. And thanks to names, we're able to capture all the information that we need. So we don't need a special data structure for trees, types, and definitions. They all the semantic information there is modeled with names. So that's the first point that we've been able to make with first-class names. Then, along the same lines, names will be our vehicle to implement hygiene. This is something that's currently under development, so I cannot show you a working example for that, but we are fairly confident that we'll be able to pull this off. And finally, and this should not be underestimated, well, I have some experience with Scala Reflect, naturally, and I've got pretty used to these manipulations with symbols and types and so on. But after working with scala.meta, honestly, now I'm just making mistakes in my macros that I write for Scala. It's just too hard to juggle all these different concepts. So personally, I'm looking forward towards having scala.meta in production. All right. Now let's see how all these theoretical things translate to something in practice. And let's try to do not something like macros, which we've seen probably a million times, but something that's currently not very possible with Scala Reflect. So let's take a program, and this is, let me increase the font. Okay, that should be better. And this is an example that one of my students, Mathieu Demarne from EPFL, this is one of the examples that he's come up with for his semester project report. Migration, code migration. So here we have an extremely naive example of some actor that was written against the old API, the old Scala actors, which were deprecated in Scala 2.10. And we would like to write a tool that would take this file and then automatically migrate it, well, of course, best effort, to akka actors. And that would entail doing something like this. Replacing this act method with receive. That would look something like this. And then we would also like to rename Scala actors to akka actors, this import here. So quite a simple manipulation if you do this as a human, but when you try to automate it, you may face some problems. So first of all, let's try to do this with Scala Reflect, and that will hint us at the possible hurdles. So let's create a program that uses toolboxes. Okay. So now we're creating a toolbox. Okay, we can do it like this. So in order to create a toolbox, you need a mirror, which is created from a class loader, and then you can say this. Now you can do something as simple as, let's just, for the sake of the example, just copy paste this code here. And then you say toolbox.parse.code. Let's see what we will end up with. So I'm going to compile and run this thing. Hopefully it shouldn't take a lot of time. And the result is actually quite interesting. So we took the code that looked something like this, just a definition of a class with some primary constructor and the while loop, and then we simply parsed it here with a toolbox. So the output that we received is very curious. We've got some val here. We've got a method called init, and the while loop is gone, replaced with some desugaring. So internally, Scala compiler very early, when it parses while loops, it replaces them with labels and then go-tos. So that's kind of interesting from a compiler writer perspective. But of course, as someone who wants to just migrate their code base to the new version of the API, that's not very relevant. And as a result, if we try to make sense of this code, if we try to transform it somehow, you can see that it's quite hard. So let's take a look at how it's done in scala.meta. So this is the same code. Okay. So we start with something really simple. Pulling something like that off, it needs only 2 imports. So one import for the scala.meta library, which is the collection of platform-independent APIs, and another import for the Scala host, which is the implementation of these APIs for the Scala compiler. If we're going to have a different version of the compiler, then we will just replace this line of code with something else, and we won't have to do anything else. So our program will automatically work with another host because it is shielded from platform-dependent details by this very layer. So now we have, we see the build, and here I've already prepared some configuration. So we will have our source path here, and we also have a class path which includes a Scala library, Scala actors, and then the compiled project. So let's go to the Echo project. Oops. Here we go. So you can see that we have this test.scala here. Oops. That represents the code that we want to process. And now we just compile it. So what's interesting about scala.meta is that it remembers all the semantic information, all these details about formatting of the code and all the semantic information. So it remembers it, figures it out during compilation, and then it saves it. So probably during yesterday's keynote, you've heard that Martin mentioned tasty, the standard for saving abstract syntax trees in class files, and then distributing them everywhere so that any tool can read it. So we're definitely interested in that, and actually since tonight, since maybe 5 a.m. today, we are compatible with that. So as I mentioned, we've just compiled this file, and now we're going to see firsthand how this tasty thing looks like. So we're going to just open this Java P and ask it to decompile the Echo class. So what we see here is that we've got a new section in the class file, which is called tasty. Mind the length for now. The implementation is by far not optimized, but I just really wanted to show it to you today. So here we have some binary information that somehow encodes the trees with all those details that I mentioned before. And now, once we have class files with this information, we can read them from a standalone tool. And this is what I'm going to show you right now. Let's start with this. Okay. So now, after I reset my Git to a different commit, we can see how it goes. Maybe we can slow down a little bit. So we create a project context that I mentioned before. And for that, we need a source path that is a directory that contains the source files. And we need the class path, which we have helpfully assembled here. So once we know all that, we can create this project context, and we can just simply ask for sources there. So what's it going to do? It will parse the files on the source path, and then it will also go to the class path and see for class files with this tasty attribute. And then it will merge the parsed files with the semantic information that's stored in tasty. And let's see what happens. Let's see what it's going to print. So we're going to package the project. Let's give it some time. And now we're going to run it. So once again, we will go and parse the files. Then we will take semantic information, and then we will merge all that. So as you can see, this vastly differs from the results that we got from Scala Reflect, in the sense that the classes, they're written just as the user wrote them, without any synthetic constructors or something like this. So we have while loops that are untouched. And most importantly, something that we haven't seen before and we didn't actually care, we got all the formatting. So we have comments, we have indentation, comments again. This is something that you cannot get from Scala Reflect at all. And now, if we're ready to tolerate a bunch of output, I can also demonstrate you that this tree also contains semantic informations. So it's not just syntax, it's not something that you can get from the parser, but actually all the references there are resolved to concrete definitions. So here we can see the same tree, and this is the raw representation, the internal representation that Scala.meta uses. So of course you don't need to understand that, but what you can notice is that here next to names we have this square brackets that we've seen on the slides before. And the square brackets, they denote resolved names. So for instance, Scala here, it represents the package Scala in the root package, and so on and so forth. So as you can see, there's quite a bunch of those things. And well, yeah, even such a simple program, it contains a lot of information. Okay, let's just move on. And let's see how we can write our migration. So what we're interested in, okay, let's see. Mm-hmm. Okay. Let me try something else. Okay. So what we're interested in is taking the abstract syntax tree that represents the program, and then finding out a class that inherits from actor. So we take apart this class, we get the list of parents from there, and then we just ask for the types of these parents. And if this type, it corresponds to Scala actor's actor, then this is something that we have to rewrite. And this is something that we will transform in the subsequent comments. Okay. So what happened here is that we go into the template, that is into the list of statements of the class, and then we find a method that's called act. And then inside this method, we see a call to the receive function that takes a partial function. That is, again, just to recapitulate, so we look for a method called act, and then this method, it should call a method called receive with this partial function. So what we need to do, we need to extract it. So we need to get rid of the loop, we need to get rid of receive, and just to get this partial function. And that's what this code does. So let's try to see what's going on here. Again, we compile and run things. And here we go. So that's the first part of the transformation. We just took this partial function. We created a completely new method. And take note that we didn't lose this comment. And also, when we inserted the existing partial function into the synthetic tree, the scala.meta framework, it actually was smart enough to de-indent the code accordingly. Of course, this is based on heuristics, and later on we will probably make this configurable. But still, for default settings, I think this is quite interesting. And again, the formatting of the parts of the program that are unaffected, like here, for instance, like the comment, it's untouched. So I guess this is more or less it, and we're going to need the final step. That is to rewrite and import. Okay, oops. Oops, that was Russian. All right, so just one single transformation is necessary to handle all the imports like we would like to. So of course, this is a bit hand-wavy, so it requires more thorough treatment. But as you can see, what we match against is an import, which has a wildcard after it. So if a reference in this import corresponds to Scala actors, then we just replace it with Akka actors, and we're done with it. So let's just see what it prints out, just to make sure that it works, and we will continue with the presentation afterwards. All right, so as you can see, Scala actors, they have been changed to Akka actors, and the act method, it has successfully been migrated to receive. So all that we achieved with like 20 lines of code, plus or minus of this transformation, plus the simple MK project context. And ultimately, all that, it has become possible because we support AST persistence. So this is the kind of model, when I said that we're especially interested in enabling novel tooling, that's what I had in mind, and that's, I think, what could be useful. So instead of the traditional model where you have a compiler plugin and then you run the compiler with your compiler plugin enabled and then you do something, we can shift to something else. So we can compile stuff using our plugin that saves tasty things. And then any tool can run on the results. of the compilation. So you can really take these class files, you can publish them somewhere, and then someone else could read it. So this process is decoupled. All right, so I've got only 5 minutes, and then let's move on. Okay. So roadmap. Let's go a bit, just a bit into the history of the project, and then I'll tell you what's going to happen soon. So well, a year ago we've announced scala.meta in Berlin, and there the idea was to have some sort of a completely empty project, to start from scratch, to start decoupled from any compiler internals, any existing implementations, and design a metaprogramming API that would be simple to use. And I hope that I've convinced you that with today's examples that we're, well, at least close to our goal. And of course, to figure out how to get there, it required a lot of experimentation. So when I was composing the slides today, and I went through the list of the projects, through the list of experiments, semester projects at EPFL, and just some random collaborations, I was amazed that it's quite a lot. It doesn't even fit into these slides. So we've seen how to build better trees. We've seen how to build a parser that supports these trees, and what abstractions we need at the foundation to make it possible. We've seen how to do better quasiquotes and how to do simpler to use semantic APIs. We've also experimented with persistence interpretation and tooling support for macros. So that was a lot of stuff. And of course, well, it took a lot of time. But now, I think, we've arrived at some sort of a sweet spot where our experiments, they really paid off. So actually, there are people out there who are already using scala.meta, and these concepts that I introduced with tokens and names, they're not just theory, they are quite useful in practice. So thanks to our collaboration with Codacy, who've actually recently posted some of their examples of code based on scala.meta, we've been able to refine our ideas and make them, well, ultimately useful for the general public. And now we decided that this is quite a good moment where we put the experimentation on hold and just push for the release so that you guys can make use of the APIs that you've seen today, and you can experiment with new tools that can be built on thanks to Tasty support. And that's the focus of the 0.1 release. So just support for Tasty, write into Tasty, reading from Tasty, and then exposing all the syntactic and semantic information that's there in the program. So if you're interested in more details, you can take a look at our issue tracker. I have the list of issues there. And what I'd like to mention in a separate slide is that there are some issues over there that actually could make use of some external help. So if you would like to experiment with the metaprogramming API, which is convenient and platform independent, maybe you could go for these issues, one of those issues that are labeled with the contributor alert. So currently we have only a few of them, and they have extensive descriptions, especially some of them, like this one. So maybe that'll interest you. Okay. Oops. That's not right. Oh, that is. Okay. So just as a conclusion, we've seen that we've tried to build, just from the ground up, we've tried to build a complete and comprehensive solution to metaprogramming that wouldn't require its users to know about compiler internals, and that would provide a wealth of information that's there in the programs. So our key innovations here are new abstractions for such a metaprogramming API, namely tokens for syntactic APIs and first-class names for semantic APIs. And now, after getting these fundamentals done, we're pushing for the release. So you can join us at Gitter, where I'll be posting our progress. You can see what issues we're working on, and just, I don't know, maybe contribute a bit. So thanks a lot, and I hope that next time I will provide more updates on the project. Thank you. All right, so my timer says that I have only 10 seconds. So maybe just one question and the rest offline. Okay.
Hey, Eugene, can you skip to slide 43, please?
Yeah, sure.
Okay. What happens with this defs method if apply is overloaded? In the compiler, you got some overloaded def type, which was like completely dangerous and useless because it was never expected. How do you deal with this issue here?
So actually, here it will be an error. So if you ask for a method, if you ask for a member with a specific name, then you're sort of manifesting that you expect a specific method, just a single one. Of course, there's a method called defs that you can use to get all the defs, and then you can filter them against the name. Okay. So a quick answer, that will be an error if a method is overloaded. And we're really interested in robustness so that we don't trick you into thinking that it does something that you don't think.
Thanks.
Sure. All right, so I guess now the time's over, so please catch me if you're interested in more details. Thanks again.